Good morning, ladies and gentlemen of the board. We're Group 33 and we're going to present to you our strategic approach in order to help Floricot achieve their short-term goals. But in order to look into the future, we must look where we stand right now as a company and our background. Floricot S.A. is a private company that operates in the Ecuadorian flower market since 1994. And throughout that year, they have expanded throughout all the mountain range in Ecuador. And right now they count with 6 farms all over the region.
We're going to use a mathematical technique called linear programming that is used to maximize or minimize objective function. That is part of a larger area of mathematical procedures called programming. Now our friend Stalin will help us saying the structure of this.
The basic structure of a linear programming problem starts with an objective function created from the decision variables found in the problem. The objective function is the function that is intended to be maximized or minimized inside the problem. Then, a set of constraints, which are equations or inequality conditions that the decision variables must satisfy, and furthermore, a feasible region, which is the solution set of points with coordinates x and y, defined by a system of linear inequalities, which will be the intersection of all the solution sets of all the inequalities.
And right now that my partners already presented to you what's linear programming, we're going to transform this mathematical tool in order to help Floricot by maximizing its benefit. We're going to do this by calculating how many boxes they should produce per week, but in the different products in order to achieve this goal. This is a problem that we wrote, and if you want to look at it, you can pause the video or you can look in the presentation in front of you.
To construct the objective function, we have a set of decision variables which are x, y, z, t, and w, and s, and then we have their descriptions, which all of them is the number of boxes of each product sold per week. The products are Gypsophilia, Hypericum, Scabiosa, Sunflower, Solidago, and Roses. And also we have the profit, which we're going to try to maximize, taken from the difference between the cost and the prices. Here we arrive to our concluding objective function.
After we have our decision variables, we're going to identify the set of constraints. So the first constraint that we have is capacity. Cotacachi's farm counts with 18 acres of capacity. It has 500 workers and it has to ship a minimum number of boxes of flowers due to the high demand. It also has an export quota imposed by the Ecuadorian government in order to protect the flower market. We're going to use that tool from Excel that is called Solver in order to find a solution for this problem. The first thing we have to do is establish the objective, then the purpose, that is maximized in this case. We're going to choose our changing cells that are the cells of our variables, and then we're going to type on the constraints that we have. The method that we're using is simplex LP. Then we could do to solve.
And now Solver has given us the solution. We must produce 30 boxes of Gypsophilia, 28 boxes of Hypericum, 77 boxes of Scabiosa, 25 boxes of Sunflower, and 25 boxes as well of Solidago, and finally 24 boxes of Roses. We must take into account that they must be produced per week, which give us a benefit of $24,791 per week in revenue.
So we only use 5 acres of land. We use our whole number of employees that are 500, the number of boxes that we ship, and we did it below the export quota with a number of 209.
The concluding analysis of this problem shows the optimal values which Kurt already showed to you, and we advise Floricot to invest in human capital and to boost their productivity, hire 25% more of the employees to their Cotacachi's farm.
Thank you very much for your attention, and we hope you take into account our recommendations.
Remember, we're Group 23.